Minasan hajimemashite. I will talk to you today about the applications of real-time simulation in power system and focusing mostly on HVDC systems. So it will follow very closely to what Professor Watson presented. Following his presentation, where there will probably be DC everywhere in the future, including DC breakers and everything DC, I just need to mention that many of this work are being done using our simulation tools at Opal RT, and simulation is being used to check for the feasibility of the concept, but it's also being used later to test the real DC devices if they're working or not. So my presentation will focus on application, but just give me 2 minutes to introduce Opal RT for those of you who don't know us. So Opal RT is about 25 years old, and we are from Canada. We have many customers worldwide, so a company of about 450 people. And worldwide, we have more than 2,000 customers, basically pretty much evenly divided in universities, industries, and R&D organizations. So we are specialized in real-time simulation of power system and power electronics, which obviously are our biggest markets. We also have customers in aerospace and automotive. Everywhere in the world, we actually have representation because we have offices in many locations, and in other countries we have distributors. In Japan, we're working with a company called NEDO, which are located in Nagoya. Here's a few of customers that you've probably know. Power system companies are over here. We have R&D centers over there. So I'm going quickly because I want to focus on the application. Some universities, we have a long list on our website if you're interested. Okay. So first of all, we have to talk about simulation. I just want to be clear about what type of simulation we're talking about. Usually when we talk about simulation, there are two different kinds. You have offline simulation and real-time simulation. Offline simulation is what you have when you are doing a simulation on your laptop or on your computer, where you simulate everything. An example of this would be MATLAB Simulink, or a PSCAD, or EMTP-RV, or a PSSE, Dig Silent. Those software are running simulation on the computer, and it is not related to the time on the wall. That means that if you're doing a simulation case of a phenomena that occurs in 30 seconds, well, maybe it will take 30 minutes or 1 hour to calculate the result of your 30-second case. So you see, 30 seconds of simulation equals maybe 1 hour or more, depending on the power of your computer. So that's why we call that offline simulation. Sometimes we use the word MIL for model in the loop, or SIL for software in the loop, but both of them refers to offline simulation. Real-time simulation is what we call hardware in the loop, HIL, where in this case, when you simulate a system, so in this small picture here on the bottom left side, you could simulate a power grid with a wind turbine or PVs, and then you connect to your simulator a real device. The connection here refers to voltage and current signal that you are taking from the simulation and you are sending to their device. Let's say it's a protection relay. So if you apply a fault in your simulation, then the voltage and current signal will change. So your relay will react and maybe send back a signal to, say, open the line, breaker. So this, you are having hardware in the loop. So in real time, here, your 30-second simulation case takes 30 seconds. It has to be, because it's connected to real device. So here you can test real devices. And we have PHIL for power hardware in the loop, where it is exactly the same thing, but except of testing a device at 10 or plus minus 10 volt. Here you have a big amplifier, and you could test device at hundreds of kilowatt or even megawatt cases. So please just keep this in mind when I talk about offline simulation and real-time simulation. Opal RT systems are used in many topics. You have a list over here, and the point being that if every system that is actually implemented in the grid starts with a simulation. So first, there was a simulation of the feasibility study. Is it possible to be done? You try new algorithms and you improve it until you have a prototype that you test and then you install on the grid. I will come back to this later. So first, we have a case in China, CIPRI, who are using our systems for MMC HVDC links. You can see on the map below that there's a lot of HVDC systems over here. Most of them are being used running MMC topology, some of them as high to 1,000 cells. So all this is being done with our simulation tools. Well, the map of where those some of them are located. This includes the first multi-terminal MMC HVDC in the world, which is 200 megawatt, 160 kilovolt. It's important to notice that this is quite difficult in terms of result, because there's many suppliers that were working together and they all need to share the result and the communication. So when I'm talking about feasibility study, I'm sure all of you here heard, or you should have heard, about the V cycle. The V cycle refers to the system where we follow the path from the top to the bottom and then go up again. At the top here is more about doing preliminary simulation, checking if algorithms are good, testing devices. Eventually, you have a prototype. So that first prototype, you're able to do hardware in the loop system. And then you do test, you implement correction because you find no problems, you get it better, and eventually you integrate it into the real system on the grid. So you follow the V cycle of the system and at each step of the way, you are using simulation tools to validate that. So here we have another MMC model, which is again coming from China, which is between Jinyu and Zhucheng. This was done many years ago using simulation tools. I'd like to show this picture because during some of the tests, of course, you do a simulation. You always simulate a three-phase fault or a DC fault to the ground to see the reaction of your controllers. Well, this is how they do DC fault. They actually threw a piece of metal and you see the arc coming from the ground overhead until reaching the MMC terminal. So this was very impressive to do. So we have another MMC system. It's again in China, but another company. And there's a racks over here, at least 50 racks of communication and equipment that are connected to our simulator to simulate the topology of the MMC. Of course, here you only see two levels, but the real system has, we have many different levels, 100, 300, 500, and thousands of systems. This slide shows the simulation result between the field test on the right side, when there's a deblocking of the MMC valve, and the simulation result of the same test. So you can see that the simulation result were very accurately showing the exact same result as this. And because of this, most projects were able to be implemented many months ahead of schedule without any problems. I say that to all my customers. Finding problems when you're doing simulation, even if it's hardware in the loop or power hardware in the loop, is much easier to solve. Because if you have problems in the real world, well, first of all, many people will have no electricity while the problem is fixed. You damage equipment, maybe some things are on fire. So finding problem in the lab is much easier to fix, and having accurate simulation result is an answer to this. We have another HVDC link example between France and Spain. This link is a standard HVDC, not an MMC model, but a thyristor-based system. You have the topology over here. And I would like to show you that here is an example of the result between the simulation and the HIL implementation. And even if you focus on the blue circle over here, which is zoomed out over here, you see that even all the fast transient are very near, so the simulation result is very accurate. Remember to keep in mind that all the simulation I'm talking about is what we call electromagnetic transient simulation, EMT. It is not phasor mode simulation or load flow simulation. That's too simple, and with power electronics, those results in load flow such as PSSC or Dig Silent are not accurate. You need to have EMT simulation. So this is an example here, again, using the same link. You can see that when the converter is deblocked, we also have an exact same results, even at the surge arrestor level between the simulation and the real operation. That thing, there's another one, again, between France and UK, you can see on the map over here. That link is 2000 megawatt, you're working at 270 kV, but the complexity of this link is that the cable underground has a very long portion, which is submarine. So you have 26 kilometer underground on both sides and 45 kilometer submarine, which is not difficult in terms of simulation, but it's difficult in terms of finding the correct line parameters to be simulated. If any of you have experience in that, line parameters are quite difficult. Using this topology, and you see the fault was applied on this side here, on the AC side, you can see that the DC voltage of the pole between the simulation and the result are almost exactly the same, and the current. So here you have the DC voltage, the DC current, the result, and the alpha angle of the controller is also very, very, very similar in both cases. I'm going now to Canada. I was working in Hydro-Quebec before, so I have a good knowledge of this. On the province of Quebec, which is I am put in black over here, we have one region which is called Gaspésie, which is the red area. It is near the sea and there's a lot of wind over there. So it's an ideal place to have many wind turbines. So if you look at the zoom of this area over here, you can see there's many turbines shown here, but each turbine is actually a wind farm. So each turbine represents 40, 50, or 60 turbines. We have simulated the entire topology of this, including the full transmission network with all the voltage level, because those lines are very, very far from those who are good in geography. You have the city of Montreal and Quebec in the bottom over here. So between the main city and the population and the big load, you have 1,000 kilometers of line coming through, and those lines need to be series compensated with SVCs, so they're 60% compensated. Many substation, many transformer, 2 HVDC link. Hydro-Quebec has a lot of HVDC on its grid. So all of this is being simulated into the schematic that you can see over here. And even in this complex system, Hydro-Quebec relies heavily on simulation results. Actually, there's a rule in Hydro-Quebec. Every device, whatever it is, as simple as a protection relay or a PMU, or up to a complex SVC controller or HVDC controller, every device must pass the simulation tests in the laboratory before being implemented on the grid. So this is an example of this, and with this complex network, you can see that a 6-cycle 3-phase fault to ground, the results of the simulation and the real-life network are an exact same results in transient. That's quite impressive considering the simulation size that we have here. So keep in mind here, we're talking about all the example I said were HIL simulation, but now we'll move a bit to a power HIL system. So here we have an example coming from France. Simulation, the island of Guadeloupe, which is an island in France, and they are having a big problem because the system is unstable. And what they actually have is that when there's a fault on the grid island, the frequency of the grid, which is 50 hertz normally, goes down to 48.2. And when it passes the threshold of 48 hertz, then there's a cutoff and the island cannot sustain that. So they needed to find a solution so that when a fault occurs, this threshold is not met. So the solution was to install a supercapacitor and see with that supercapacitor if it could provide power to keep the frequency high enough. So this is the topology of the simulation case, and I just want to highlight that here you have the simulation tool with a small amplifier. It's only 15 kVA and connected to real devices. So you have a real turbine, a real supercapacitor, each of them with their converters. And using this setup, they were able to make studies. And there you have the result. In red is the new frequency deviation when there's no three-phase fault. And you can see that with the supercapacitor, we don't reach the cutoff region. The blue was the original problem. So clearly, we solved the problem. Well, not me personally, but our customers solved the problem with our tools, and this is a very, very good success story. We also have another customer. Again, this is in Germany, I think. They're testing a PV converter. So the inverter, you have the cell here with the inverter going from DC to AC, and then the amplifier in a simulated grid. And the aim of this study was to test how to manage the voltage level, because in the grid that you see over here, you have a 1, 2, 3, 4. The voltage at each location was very, very unstable and moving. So what they actually did, you have on the left side the original problem, and on the right side the solution. So you can see that here the reactive power of the area number 4 was positive, which was causing a lot of trouble. Once they adjusted the inverter and tuned the algorithm of balancing with the simulation, you can see that after the fault, everything is negative, and this was acceptable to them, and hence the solution was found for this issue. This is another example. Probably Professor Wilson would be happy to see this. We actually have a customer. It's a joint work with RTE, which is the utility in France, and a few universities that are simulating a DC grid. So you can see that in blue is the simulation. Everything is being simulated, including the converters. And then they have 5 amplifiers that each of them convert the AC. In some cases it's AC, because here you have a real converter, but this one is simulated, in order to create a DC grid. So in the middle here, the whole grid is in DC. And the purpose of this study was to see how to synchronize all the converters in order to have a steady HVDC level. It's written over here. You could read it later. Sorry, I'm going quickly because I have many cases I want to show you. So you can see on the left side, the DC voltage was very, very unstable previously. Whereas after implementing the synchronization algorithm between the converters, the DC voltage is very, very, very nice and beautiful. I want to finish with a very good example here. This is an example of a paper factory that we implemented in Hydro-Québec a few years ago. As you know, well, I don't know if you know, but as you should know, paper is a big business. There's Canada, we have a lot of trees, and we make a lot of paper factories. And in a paper factory, there was a new factory that wanted to open, but in order to open and create all the jobs, they came to see the utility company, which was where I was working previously, Hydro-Québec, and they said, we will make a paper factory if you can prove to us that the factory must operate if you have a two-phase fault on the grid. So they said, even with the two-phase fault, we don't want to have a factory shut down. We want to make sure everything is working. So people of you who know, paper factory has many, many DC motors. If you see on the picture over here, all those motors that are turning the paper are all direct drive motors. There is no gearbox, which means that the speed of the motor is directly proportional to the voltage level. And of course, the papers they're turning very slow. You're talking about 100, 500 RPM. It's quite slow. And the reason for this is it's quite simple. So you see here, you have the paper paste that is being outputted from the industry. And then in order for this to go from the paper paste up to nice paper, it goes through many, many rolls. So you see the yellow line over here. And those rolls are heating and are compressing the paste to make paper. And then you have many, many like this, where the paper will dry. They're checking the water percentage of the paper until it's ready to go. And if you have a small voltage deviation or a two-phase fault or even a one-phase fault, then what happens is that DC motors over here will have differential in speed. And that change of speed, that sudden change of speed, will actually break the paper. So you could imagine that all the paper going like this eventually goes somewhere, and then they have to stop the factory, shut down everything, clean for 4 hours, and restart again. So that's why the big issue is we need to make sure that the speed of the motors does not change when there's a fault, because we don't want to restart the factory. So you have here the representation of a motor. Remember, those are direct motors, they're not the drives. So in order to, I'm explaining this to you because I also want to show you the process when you're making such a study. I think it's important for engineers to understand about that. So first of all, you say, okay, our first problem is we need to simulate the grid. So you simulate the AC grid. This is what is done in this area over here. This is a simulation of the grid near the location of the power plant that is planned to be implemented. So although it is simple, it is technically accurate representation. You have to note that the lines and the loads, everything is made in order to represent the poles and the zeros of the grid at that location. After that, once you simulate the grid, then you have to simulate the plant. So then we have the top right side here. We simulate the plant, which is working at 600 volt. There's no need to simulate 25 motors. So there's only one motor being simulated and some filtering, obviously, for cleaning all the harmonic. And then at the 25 kV level, the solution that was thought out by the researchers was a DVR, which is a dynamic voltage restorer. Basically, it's when you have a fault, it quickly turns itself on to inject power very quickly, and then when the power is coming back, it will turn off. So it's like an emergency power supply, but for a very short period. And so this model was implemented also. Note that this study I'm presenting up to this point, previously the cases were HIL. But in this case, it's only MIL, software in the loop, only simulation, not a real one, not yet. So once you have the whole model over here, then you're able to test to see a two-phase fault without the DVR to see the issue, and then with the DVR. So later, when the study can be okay, you can take the DVR specification to a manufacturer and then test the DVR in this scenario. So I'm going to show you the results that were obtained over here. This is the simulation result. So you have the voltage at the factory, which is very nice. Now there's no fault, everything is good. You see the DVR, you think it's working, but actually this is 0.1. It's very, very low. So it's just like 0. And no fault, nothing happened. So you look at the DC motor volt current, it's very, very steady. And the motor speed is very, very stable. So when you do a fault, then this occurs. So here we apply a two-phase fault. So you see that at the 25 kV bus, you have a two-phase fault. So you see phase A and B are going down. Phase C is almost not affected. So at the plant level, you can see that you have some harmonic content, but still phase B and C is not good. And this, again, the DVR is off, okay, 0.2 volt, don't forget about that, it's 0. The zooming is not correct on this picture. And then you see what happens when you have a fault in the DC motor. The DC motor, which was stable first, has a sudden drop down, and then some harmonics, and then when the fault is cleared, it's going back up. And this change in motor current makes the speed of the motor go down by about 20%. And this creates what I mentioned before, the paper breaks in the power plant. And then, the factory shut down, have to clean everything, and everybody's angry. So if we repeat the same simulation, but with the DVR, now you see that we apply the same fault. So we have the same fault over here at the 25 kV bus. The voltage at the industry now is almost perfect. You only see a little bit of overshoot here. And why is that? Because now the DVR came into power. You see that the DVR was off, the fault occurred, the DVR injected the current to compensate for the two fault. You can even notice, some of you who have good eyes, that phase A and B are higher compared to the phase C in order to have a perfect three-phase result. And because of this, the DC motor in the current has a small transient, but still, even with that small transient over here, now the speed of the motor doesn't change as much as before, and hence the factory can sustain a two-phase fault. So the problem is solved, and now everybody's happy. We'll have a new factory, there will be new jobs, and everything is good. So this is to show how a simulation tool, good simulation tool, can help solve real-life problems and fix them. So this is only to show you the difference between before and after, but it's same way form I showed you before. I always like to finish with this slide, which is the IEEE smart grid domains and subdomains. This is only to show you that simulation tools, today I talked about HVDC, but simulation tools that can be used for everything. You can use them for power quality, you can use them for protection, obviously. You can use them, now a lot of customers are using this for EV, to see either for the EV itself, like car makers, or for the EV seen from the grid. By this I mean if you have one car is 100 kilowatt and you have 1 million people who are connecting their car for charging, well then you need 10 gigawatt of power. So the grid has to be able to support that. The distributed generation, you have transmission, all the topics over here should be, simulation tools should be used to be able to study that. So as a conclusion, simulation tools are capable of performing offline simulation, and hardware-in-the-loop simulation are essential to cover all phases of a project, from the original ideal to the concept, to the prototype and the final system installed on the grid, making the commissioning much faster. EMT simulation is the only method to accurately reproduce a real-world result. Please remember this. Usually in the presentation, I talk about automatic testing tools. Today I had to skip that because of time. Maybe next time we'll be able to talk about this, but automatic testing tools are essential because studies in power system are actually statistical studies. So when you have a fault, you don't simulate one case of a fault at 100 milliseconds and it clears at 200 milliseconds. You have to check fault at 90 milliseconds, 91 milliseconds, 92, and you cover all the range. And the same thing for the clearing. So you will need hundreds of thousands of tests to be able to guarantee the result. And people tend to forget that, especially the younger engineer. And also the guaranteed method for grid owners is to perform HIL testing of all devices before installing on site to reduce cost and risk of failures. 皆さんありがとうございます。